Okay, relativity, special relativity. You have to know general relativity in concept, but not mathematically. Special relativity you do have to know mathematically. There's a lot of places you can go with relativity, and it can get crazy. And I'm happy to have those discussions with you. But first, I just want to show you, this is what IB wants you to be able to do. Okay? So, Panise is here on the spaceship. John's riding on the top.
So John?
Yeah, I got a VIP, you know.
VIP?
He doesn't need a space helmet. And Panise has in the spaceship a laser pointer. Okay. And she fires the laser pointer from the ceiling down. We're going to do the simple version of this.
Oh my god, you okay?
And that's it! I've always wanted to do that, actually.
It's super fun.
Wait,
Have you done it?
Yeah.
You smashed the guitar?
Yeah.
Oh,
I smashed my guitar.
that's pretty baller.
Clash.
Well, it was like my dad's old guitar, and it's like, here, have it. You can do what you want to play.
I'm sure that's what he had in mind.
I played it for a while, and then I got bored.
Okay, Panise has a laser pointer, and she's gonna shoot it. That's what a laser pointer sounds like in space. It's going to go straight down and hit the bottom of the spaceship.
Yeah.
And so, for Panise, she's going to see this travel at what speed?
Speed of light.
Speed of light. And so, this we would say is the distance it travels is the speed of light times time.
Yeah.
Right? Okay, so let's call this C times T. What subscript do you want to use?
X.
P for Panise, A for astronaut, S for space. P for Panise? So this is Panise's time, okay? Now, this is where relativity is... Thank you. Thank you, Karush. It's weird, right? Because you've lived your whole life and you've never thought about... There's some things in your life you've never thought about changing, right?
No.
So obviously, it can seem like time goes faster or slower, but that's not what we're talking about. We're talking about time itself can be different if you're in a different reference frame. Everyone say reference frame.
Reference frame.
Jackie, what do I mean when I say reference frame? He's like, I don't know. Okay, that's fair. Anybody have a shot at it? Arvin?
Like, from my perspective versus an observer.
Yes, exactly. How could Arvin's frame of reference be different from Leo's, let's say?
It's like the shadow of Mr. Smith.
The shadow of Mr. Smith. Okay, so I would see them in different places. Like, they're in different places right now, but are they in different reference frames?
No, they're in the same one because
No, it's
they're
in one place.
all.
You're in different places, but you're in the same reference frame.
We're all in the same.
David, say that again.
You're going at the same speed.
They're moving the same speed. We're all in the room here. The room, we could say this room was moving, right? If you were standing on the moon, you would see us moving that way,
Yeah.
1,700 kilometers an hour.
Wait, what?
Because we're on Earth.
Earth is moving.
Earth
Oh.
is moving. we're
Sun
all
comes up
moving.
in the east, right?
Yeah.
That's really because we're spinning, the Earth is spinning that way.
Mm.
If you're standing on the sun, you'd be crispy and dead. But if you were standing on the sun, you would see us moving even faster, revolving around the sun, right?
Yeah.
So it depends on where you're looking from, what you would say we're doing. If you're in the room, we're all sitting still, right? So we're all in the same reference frame because, as David says, we're traveling the same speed. As soon as Panise takes off from the Earth, she accelerates away from us, right?
Yeah.
So she's in a different reference frame. If we're all down here, we're sitting in class, wishing we were on the spaceship with Panise. Our reference frame is different, right?
Yeah.
So our time, let's say our time equals what? T what subscript?
T,
C for class?
yeah.
Class.
Okay, TC. That's our time.
Yeah.
Now this is weird because TP, so for Panese, time equals time Panese. This is a weird thing, right? Every piece of physics you've ever done, all the Newtonian stuff, times time, it ticks exactly the same.
No.
But this is where special relativity is weird, because Einstein came along and said, well, actually, time is a matter of perspective. It depends what you're doing. Time itself can change. Okay?
So do we each have a different perception?
Well, you're not all of us.
Do we each have a different?
Joshua, go
Do
ahead.
we each have a different perception of time?
Right now, we all have the same perception of time. But if I'm running, now my perception is different. I'm not going fast enough for that to be significant, but that just took me a little bit less time than it took you. So I'm like a little bit younger than you are right now.
What?
No, that's not true, because I'm super, super old. But I'm like, relative to what I was when I started running,
You're a little young.
I aged a little bit less than you did. And if you get on a jet plane and you fly around the Earth, this is the Hefele-Keating experiment. I'm jumping ahead here a little bit, but
Yeah, go ahead, go ahead.
this is a real thing, right? So the Hefele and Keating decided to test Einstein's theory, and they had two atomic clocks. They run on the oscillations of a cesium atom. Really, really precise clocks. They let them sit there for quite a while and just tick, 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 and they're super synchronous. No deviation of time.
Yeah.
They took one clock, I think they had 4 clocks actually, and they took 2 on a plane, and they flew around the Earth. And when they got back, the clocks were different times. Actually.
The ones
Was it
on
by
the
second?
plane.
No, less than a second. But significant enough that you could measure the difference. A long time ago at Harvard, they put, I won't get into that.
No, do
This is something that is a real effect. We see it all the time for satellite GPS.
Delay.
GPS works where like John goes for a run, right? You set a GPS when you go for running?
Yeah.
Yeah. So he sets his Garmin watch or whatever. You got a Garmin?
Yeah.
Yeah. You go click, and he goes running, right? And something has to know where he is to get his route, right? And then it's going to give him the time. So that signal bounces off a satellite and comes back down. There's different networks and GPS and the Chinese one, all that, but that doesn't matter. Is the satellite traveling the same speed that we are?
No.
No, I don't think so.
It's geosynchronous, which means it hovers over the same spot right above us. But it's moving faster. Why?
It's traveling
Trying
faster.
to keep in orbit.
Is the radius the same?
No.
Radius is bigger, right?
Oh.
So the circle is bigger. The circle the satellite covers is bigger than the circle we cover. So it's going faster, and it's significantly faster. And so time ticks faster on the satellite than it does for us. You actually have to code in the adjustment for time. Otherwise, it's going to tell us that John's in a place where he's not. Okay, so this is a real thing. This isn't just a theoretical thing. This is a real measured thing. Everybody knows about it. Okay, so how does this work? Well, we see the rocket ship moving, right? So for Panise, she just sees the light go straight down. What do we see?
We see the light go like this.
So it's going to start off moving down, but the ship is moving.
Yeah.
So as Joshua and Croce say, it's going to go this, right? Because this spaceship is moving. At the end, we're going to see the spaceship out here, right? He's in the spaceship. different lengths, right? Which one is longer?
No,
The observer.
The one that we see is longer distance, right?
So it has to take
Okay.
more time.
We also see the distance of the ship, right? I'm gonna do this one in blue. So the ship moves some distance, right? What could we call this length that the ship moves? Sure. Just thinking
Distance traveled?
simple velocity, time, and distance.
Distance traveled.
Distance equals velocity times
Oh.
time, right? So this would be VT,
Oh.
but which time is it? Is it Benise's time?
Last time.
Yeah, that's right, John. It's not Benise's time. She just looks like
So now
she's
she's not moving.
not moving. She's just sitting there, right? So this is the class time. Okay. Okay, so I'm gonna erase this stuff because it's just complicating things. You can see that we have a triangle here, right? So simple Pythagoras, what's this end?
Hypotenuse.
This is the hypotenuse, so we could say that this is equal to,
B squared, not B squared. Plus A squared.
yeah, if we solved it, it would be the square root of this squared, right? Plus this squared, right? With me?
Yes.
Okay. That should also be equal to something for us, right?
Class.
What VT is it?
The Earth.
Victor?
Isn't CT for us?
Good, good, very good. We're seeing the light move at the speed of light times our time. Yes?
Yeah.
So the distance this travels should be C times T for the class. Okay, so I got this part just from Pythagorizing the two sides, but this is what it should equal. And that's what we're going to use to derive this formula. Okay. Now I want you to pay attention to a fact. The speed of light in our universe is constant. Okay. So we gotta think about this a wee bit here. I have a dolphin. If I throw the dolphin at 10 meters per second, it travels a certain speed, right?
Yeah.
What if I was riding a skateboard? I won't get it out, but let's say I'm riding a skateboard. I'm moving at 10 meters per second already, and then I throw the dolphin at 10 meters per second.
So he's going
What are you going to see? 20, right? I'm already moving 10, and I throw at 10, you're going to see 20.
Yeah.
Okay. If I have a flashlight, and Zane has a flashlight, and I'm moving by Zane, and I click the flashlight on, and he clicks his flashlight on, we have two lights going this way. Whose light is faster?
Things.
The same. This is weird.
Why is it weird? It's not weird. It's how's it weird?
It's weird because if I'm already moving,
It should be fast.
the light I should add the velocity I'm moving at with the light.
Right faster.
You're not throwing.
So you hand in the hand.
Well, I'm kind of throwing it. I'm shooting it out of my light, my flashlight. Well, say it again.
Shooting a
It's not you shooting out the light, it's others.
Oh, okay, it's not me shooting out the light,
Let's
but
use
is the
better.
source of the light moving in the beginning?
Yeah.
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 Alright.
What if I was going by Zane at 99% the speed of light?
No.
What do you mean?
It wouldn't change. It wouldn't change.
If what speed of light is 3 times 10 to the 8, right?
Mhm.
What if I was going 2.98 times 10 to the 8 meters per
It'll
second?
be the same velocity.
I go by Zane and I go,
The same.
still same?
Yeah.
You're right. You're right. And we've measured this many, many times.
Wait, how
The
you
speed of
measure
light
the
is
speed of light?
constant. It doesn't matter how fast I'm going. The speed of light will be the same. What that means
Speed limit.
is that time for me, as I go by Zane, has to be different.
Oh.
Time has to travel different for me, because if time was traveling the same, my light would go faster than his light.
Right.
What are you talking about?
So the only way that those two flashlights can come out at the same speed is if time is moving faster for me.
So you, oh my god.
So special relativity is all about having different times in different reference frames. If you're moving fast,
You're literally.
your time dilates. Okay, and that's what we're going to calculate right here. Okay, so how do we do this? We start with this. We say TC for the class
Yeah.
is equal to this. And we say CTP for Panese, and this is squared plus BTC for class. And then we're going to work through this. What would you do first?
Square them?
Yeah, let's get rid of that square root. Let's say this is C squared TC squared. And then we just have this left. And I'm going to square out each individual thing. Okay, what would you do next, do you think?
Take this down. The T out.
We have different T's, right?
Yeah, T class.
Can we get all the T, can we get the TPs, or the TCs, can we get these together?
Down.
No, we can cancel.
You could.
It's pretty simple.
Yeah.
TC squared plus.
You just subtract this over.
Yeah.
Yeah.
So we're gonna have C squared TC squared minus
B squared.
B squared TC squared equals B squared.
Oh, wait, oh.
Square. Okay, so I just took this one and subtracted it over to the left.
Yeah.
Okay, we want to find a calculation for Panise's time here. So I want to get rid of this C squared. How do I do that?
Divide.
Divide. So we're gonna have, I'm just gonna do this. So if I divide both sides by C squared, I have to do both terms. And then I'm gonna do two things in the next step. I'm gonna turn this into 1, and I'm gonna factor the TC squared out. Okay? So I'm gonna say this is TC squared all times 1. You get why this is 1?
Yeah, it's
Yeah.
above that.
C squared over C squared is 1, right? I factored out the TC. And then this is minus B squared over C squared. This is a handy term right here. B squared over C
What
squared.
is that? What does that mean?
Velocity over speed of light.
Yeah, this is whatever velocity you're moving at divided by C, which is the speed of light.
So what is that?
So if I tell you that you're moving at 0.9 the speed of light, then this V over C is equal to 0.9.
Whoa.
This equals this. What happens to these two C squareds?
They cancel.
They're gone, and we have
It's easy.
B squared,
This is squared.
beneath squared.
B squared.
Okay. I'm gonna move this up here. And we're just gonna do one more thing. What do you think it is?
Square root is supposed to.
Square root. And I'm gonna leave this, I'm gonna put these two together now.
Okay.
I can do that. And that's going to be all times TC, and that's gonna be equal to TP. So I've square rooted everything, both sides. And I can take this and get rid of the square on the TC and on the TP. Can they see me over here on the video?
No.
I gotta turn it. So to finish that up. It would be nice to have a time for us, right? So let's solve this finally for TC. I'm gonna leave the TC here, and I'm gonna say this is whatever time Panese has, and then I'm gonna bring this underneath.
Wait, this is time class.
Yeah.
Wait, are we looking for time class?
This is the formula for time dilation.
So wait, how much time?
Now, the naming is kind of confusing. We've said this is the time for the class, and this is the time for Panese, right? So this is the moving person, and these are the observing people. Sometimes you see this as T prime and just t. Sometimes you see, and so it looks like this. You can say, this is t prime and that's t.
Yeah.
So T prime.
You can also sometimes see it confusingly as this is t and this is t naught.
What? Oh yeah, that makes sense.
Because IB is British, they like t naught and they call this proper time.
Proper time, right?
Proper time.
Yeah.
I don't know what makes it proper or what makes it more proper than the person
Proper.
who's observing, but they like the word proper, I guess.
Royal family time.
Yes, it's very royal family. This is the royal family's time because they're in the spaceship, obviously. So they're very wealthy. They're not even British, did you know that?
Yep.
They're like German.
They must really have a laugh behind the scenes. Just like,
The Habsburg, right?
Anyway, well, I'm not gonna make fun of the royal family on
Cousins
video.
with the Kaiser.
They're not, they're not.
I like William. He's, engaged.
Windsor.
This is called time dilation.
Proper time.
It's not really a great word. It's not a fantastic name.
I think it's cool.
It gives the illusion that things just stretch out and take slower. It just takes a longer time. It's dilated. What you have to try to take in is that
It's the same time, different groups.
yeah. So is Panise going to see things happening slower?
No.
No.
Or
For her, everything appears normal, right?
It's not gonna matter until you go like.
Sheer light.
Relativity.
Yeah. So let's do a little problem here. Let's say, Panise, how long do you want to go for?
2 years.
2 years. So Panise is going to travel for 2 years.
Is there any specific unit time has to be in, or is it seconds?
No, it doesn't matter, anytime. It's a ratio, right? And let's say she travels at 0.99 the speed of light. Tell me how much time will have passed here while Panise is flying around the galaxy. You're gonna need your calculator.
Wait, what is it?
Which one of these was Panise's time?
Proper time.
Proper
Yeah,
time.
this is Panise's time, right?
Wait.
The proper time. Proper time is in the spaceship. It's kind of interesting that it's more proper to be in the spaceship than it is to be on Earth, but we'll go with it.
One line is
Next year, you'll receive one more.
Yeah, but all 0.99C.
0.8 years.
Next year. 14.1.
What is it? No, you have to times 2. What is
Yeah, 14, isn't it?
No, you just times 2.
Is it 100 and a
Yes.
half?
Yeah, so it's 0.8.
No.
100 and a half years?
No, is it without the 2 it's 7.1, I think. I think you times by 2 twice.
Just where the
So C is the constant speed of light.
So-
C is speed the person travels at.
Yeah, so this 0.99, that is V over C, right? So the way that I do this is I take that 0.99, I square it, I multiply it by -1 to make it negative, I add 1, then I square root the whole thing,
Oh yeah.
and then you flip it over.
It's 14.172.
And by the way, a way to shorten this is you sometimes see this as T equals gamma T naught. And so gamma is a short way of saying 1 over all this, and
Ah, I see.
so gamma is equal to the 1 over this bit. This is called a Lorentzian transformation. Did you get 14?
Yeah.
Okay. What does that actually mean?
Behind the people in the ground.
Yeah.
Panise observes 2 years, B observes 14 points.
Exactly.
Wait.
And does that, when Leo says we observe, does that just mean like, oh, it's like we just say it is? Or like, Panise, how old are you?
I'm 17.
So Panise is 17. How old would she be when she gets back? 19 years old. I'm 49. How old am I gonna be when Panise gets back? 63. Oh. If you guys, are you guys all 17 too?
Yeah.
Okay, so how old are you gonna be when Panise gets back? 31, right? So Panise will only be 19.
That's unfair.
And you guys will be 31, right? That's crazy. What do you think? Okay, so let me ask you a couple questions here. So conceptually, if Panise travels on like the fastest military jet that we have right now, say she's like Mach 10 or whatever, is she, when she travels for 2 years, when she comes back, are we gonna be like, oh my gosh, like we're all 100 years old?
No, Mach 10 is like not even close.
No, it's gonna be
20 seconds. 20
it's
seconds.
gonna be a small difference, right?
Wait, what's Mach 10? Don't
the-
calculate.
So that's, by the way, the answer to this is
14, 40.
14 years pass here on Earth. The graph looks something like this. If you start off if your speed is 0, and this is c, the time change looks like this. Does it ever actually touch c?
No. Well, it never.
Sorry, this is confusing. This axis is v, and this point is c. It's asymptotic, right? You can never actually travel
The speed of light.
the speed of light.
So your speed exponentially.
Your time change exponentially dilates. This is time here.
So that's time. So what is this straight line right
Here,
Just normal.
Velocity.
this is just normal, right? So if you travel super fast, like the fastest thing we can travel is like way less than this. So you're not having a big change in. They say that it's relativistic at 80. I think it's 82% that they say.
What's the speed of light?
It's about right there. Yeah, you gotta go 82% the speed of light for it to be significant in your calculations. So basically, if you calculate a velocity on an IB exam and it's like 2 times 10 to the 8, that's fine. It's not changing time enough to worry about it. If it's over that, if it's like 2.7 times 10 to the 8, okay, now you have to do some crazy things, right? Because time is not ticking the same for both the objects. So this stuff is, we would say, relativistic.
None of this works if like technically this knows Panise never comes back, but she does not exist within the same time reference service we do.
It's not gonna really matter to us.
Yeah, but she never comes back. She's like the same reference point, that doesn't matter.
Yeah, there's some really interesting paradoxes here, and I'm gonna be totally honest with you. Humanity hasn't fully figured this out. You can go online and so there's something called the twin paradox.
Alright, going
Alright.
up and then going down, they'll be the same age.
Let's say that we had a pair. Do we have twins in the school?
No.
Yes.
Yes,
Do we?
Sabrina's one.
Sabrina and Rose.
Okay, so anyways, you got a pair of twins, and we separate them. We put one twin on a spaceship, and we send her off. Okay. Imagine for a second that you're the twin on the spaceship.
Yes, let's go.
How do you know that you're moving away from the Earth and not the spaceship is sitting there and the Earth is actually moving away from the spaceship?
I can see.
You don't.
Because if you see it,
You know, because if you're completely still, the Earth's just gonna shoot.
Now, if I was going to give you the simple version, I would say, I don't know, upwards. Don't worry about that. She accelerates, so she's the one that's moving. We're sitting still, right? The trouble with that explanation, if you want to get into the real weeds, is that you are accelerating right now.
Yeah.
Because space-time is distorted due to the Earth. So this is general relativity. General relativity says the Earth is a big hunk of matter and it pulls on space-time and it stretches it. So the space-time here is not the same at a higher level than it is at a lower level. And so we're accelerating upwards right now. That's what gravity actually is. It's not a force that's pulling you down. While you sit there, you're being accelerated up. The reason you don't come off the floor is because the floor is like a rocket ship that's accelerating you upwards. So whether the person leaves the Earth or the Earth accelerates away from the spaceship is kind of thrown into a little bit of a cloud. I would encourage you to not worry about that right now. You can think about it later on May 15th. Okay?
On May 15th.
When it's a test
Yeah.
question and you're like,
No, it won't be a test question. It won't be a test question. The test questions, I can tell you pretty much what they're going to be. They're going to give you a time dilation question. They're going to give you probably some kind of magnetism question, which I will explain to you in a minute. They might give you a tunnel question, which I'm going to explain to you in a little bit. And they might maybe give you a relativistic addition of velocities question.
for P3 or just
This is all P3. So paper 1 and 2 have no options. And if you're SL, you don't have to write the paper 3. If you're SL, you don't have to do the option. Paper 3 is one database question, like a labby kind of thing,
Oh my god.
and
Wait.
the option. Now, let me be really clear right now, I'll say this on video too. If you don't want to do relativity, if you're like, I just understand engineering physics better. If you've done a bunch of torque and equilibrium and stuff, you're welcome to do that option. If you're like, I want to go into medical imaging, that's what that's what I want to do, I want to learn about it, then do that option. I choose relativity because it's the hardest, which means the exam is the easiest.
relatively.
Engineering physics is the easiest, which means the exam is the hardest.
I'm gonna give you some
They will sit there at the table coming up with diabolical torque equilibrium questions to trick you in, relativity, this is hard enough. Just give them a time dilation and a magnetic thing. That's fine. I'm gonna stop this video because otherwise it'll get too big.
It'll get incriminated.